Okay, so as I was saying, in the previous class we derived the four very important equations of stellar structure. But before that we talked about the four important assumptions. And the four equations were equation of continuity or mass conservation. Then we talked about the energy equation. Then we talked about the equation of motion, from which we derived the hydrostatic equilibrium equation, and finally we talked about the composition equations. Right. Now out of them, I think the composition equation, as you have also mentioned, it is one of the biggest in derivation. But again, composition is very important for stars. And now what we are going to do, as you can see on your screen, we are going to derive a very important theorem which is known as Virial theorem. You have already know this. You have learned this in your graduation, probably in your school days as well. Now I am not going to talk about Virial theorem in details here. When I discuss plasma astrophysics, then I will talk about the most general form of Virial theorem there. But right now, what I am going to do, I am going to derive the Virial theorem from the equation of hydrostatic equilibrium, okay, which we have previously derived. Now, if you remember, it was basically the equation 16, which was the equation of hydrostatic equilibrium, which I have written over here. Okay. Just a second. Yes, this is the equation of the hydrostatic equilibrium, this one. Now, let us multiply this equation with the volume, right? 4 by 3 pi r cube of the small r, right? With this volume, let us multiply. Then after some manipulation, you will see it is quite straightforward. We will observe that we get this relation. Now, continuing with our formula, this is equation 39. Now, this is very straightforward. Now, what I am going to do, I am going to play with this part over here. Let's see. Okay. Now, so if I play with this part, then you will see we get around like this. We can write this expression V dp in this form, and then let me again write this equation number. This is equation 40. Okay, so we get this expression, this one. Now, if we integrate over the entire star, then what happens? Then we have to integrate from the center to the surface, and upon doing this integration, which I have shown here, again I am giving equation 41 name. Then remember this, because volume is 0 at center and pressure at capital M is equal to 0 at surface. So what do we have is this expression. This expression we will have, equation 42. Quite straightforward. Here, this capital omega is the total gravitational potential energy, this one. And thus, we have this relationship. You see? Equation 43. Now this relationship between the pressure and density of a star with its gravitational potential energy is in fact the global form of Virial theorem, or basically you can call it that this is the form of Virial theorem for stars. Now we can apply this to a particular case of an ideal gas of particles. Let us apply and see what happens. So we will consider ideal gas of particles having mass small mg, and let us see if we can get a relationship between the temperature and the total internal energy and gravitational potential energy of the star. So we are going to consider an ideal gas and see if we can get something interesting. Remember that we expect হ্যাঁ বলো
স্যার আমরা স্যার ভিরিয়াল থিওরেম পড়েছিলাম যে টোটাল এনার্জিটা হয় তার হাফ অফ ইটস ভিরিয়াল, মানে তার পোটেনশিয়াল এনার্জিটা। এখানে স্যার ওই যে -0 to m gm dm r square ওইটার কি ওর ইন্টারনাল এনার্জিটা?
No, that form will come later on. I have still not derived that part. I remember the half part that you are talking about, that part will come later on. Okay, right now we are in the middle form. Now you can also get that result using a different form. I am talking about a different route. তুমি যেটা বলছো ওইভাবেও করা যেতে পারে, ওটা খুব সহজ ভাবে করা যায়, ঠিক আছে, একদম জেনারেল বেসিক স্টেটমেন্ট। আমি কিন্তু ওইটাতে এখনো আসিনি, ওটা আরো অনেক ফর্ম আছে, আমরা ওটাকে এক্সপ্লোর করব কিছুক্ষণ পর, ঠিক আছে। দেখো কি হচ্ছে।
আর ক্যাপিটাল ওমেগাটা কি স্যার?
ওই যে তো গ্র্যাভিটেশনাল পোটেনশিয়াল এনার্জি। ঠিক আছে, আচ্ছা। নাও দেখো, we expect the gas particles in the stellar interior to be completely ionized atoms. So we can assume that the gas is monoatomic. Now assuming so, monoatomic gas. Now assuming it plus ideal as well. To be ideal as well, then we have this relationship which is equation 44. Fine. Now in this case, remember the internal energy of the gas is simply the kinetic energy of the gas particles, and so we will have this relationship, this one. তুমি যেটা আমাকে বললে, what you told me just now, actually if you remember in class 12 there was this sort of expression also in the gravitational chapter. So we have already talked about the very basic form of Virial theorem in schools as well. Now, so let us apply what we have learnt just now. So we get this relationship, okay, you see, from here total internal energy, and so we get U is equal to minus half of omega. Okay, so this is what you were asking me, right? This is yet another form of Virial theorem. Now we also have to understand that there are certain very interesting aspects as well. Say for example, look at the structure of U here given by, this is equation 47 and this one is equation 46. you see, look at the structure of U over here. Now I have just calculated this. We have done the integral 0 to m here, total mass, and this is just the average temperature. So we are defining average temperature like this, equation 48. Now, so what do we have here? Therefore, we can write that the average temperature of the star from these expressions. So this is how we define. But now using this form of definition in the previous expression, we can get this result. So this is what we have for the average temperature of a star. Now, from dimensional arguments, you see the gravitational energy of a star can always be written in this form, minus alpha g m square by r, where this alpha is a constant which depends upon the mass distribution. So this depends on mass distribution, constant which depends on mass distribution. Now, for very reasonable mass distributions, you can also check yourself as well. Okay, it is observed that the value of alpha is less than or equal to 1, and thus as a result of this we have this expression for temperature, average temperature, which is equation 50. Equation 50. Now let us again write R, this R, in terms of average density, which is so if we use this average density over here, then you see we will get the one of the most interesting results for Virial theorem when applied to an, so we get this is a result of Virial theorem when applied to monoatomic plus ideal gas. And what does this show us? This result, you see, it gives you the expression for average temperature as a function of mass and average density. Now, so what happens if stars have same mass? So you see immediately from this expression that for stars of equal mass, the denser star will have average density higher, and so its temperature will be higher. So the first conclusion that we get from this result is that for stars of equal mass, the denser star is hotter. Okay, what does this mean? This means that if a star contracts, it heats up, and if it expands, it cools. From this expression, you see, from this expression, again, you see, from this expression. So what I am saying is that if a star contracts, if a star, so this is a big star, right? If it slowly contracts, now it becomes something like this. It just do not scale, I am just representing. Then the average density will be higher compared to the previous case, and so this will go up. As a result, T average will become higher. So if a star contracts, it will heat up. Now again, what will happen if the star expands? If the star expands, then again the average density will go down, and so the star will cool down. Understand? So this is another observation. So this is observation 1, and the next observation is that if a star contracts, it heats up, and if it expands, then it cools. Okay, now you can ask me questions.
স্যার বামন গ্রহের ক্ষেত্রে যেগুলো মানে টপ স্টারের ক্ষেত্রে, ডোয়ার্ফ স্টারের ক্ষেত্রে, স্যার ওখানে তো স্যার ওটা কি স্যার মানে ইন্টেরিয়রটা থাকে আর এক্সটেরিয়রটা বেরিয়ে যায়?
Now I'll talk about again. I will talk about it later on. Let me finish the stellar structure, because dwarf star. What is a dwarf star? You know?
হ্যাঁ স্যার, মানে স্টারের যখন কোরের মানে
Just a second. Just a second. Yes, yes. I will clarify it later on, because otherwise my entire rhythm of how I have prepared this course for you will be spoiled. Okay, I'll come to this point. What happens now? This is the case for a normal star. What happens for a neutron star, for a white dwarf star? There are also dwarf planets as well. Okay, now we will talk about it later on. Right now, let me talk about this, what is present before you. Do you have anything to add, or if you have any questions regarding this, then do ask me. No, this process doesn't happen in the case of dwarf that you are talking about. No, I will use when I talk about star formation, then at that point I will tell you. It's somewhat similar, but again very much different as well. Okay, now fine. So if there are no more questions, let me start the next part. And what is it? It is, so what we did after deriving the 4 stellar equations, we used the equation of hydrostatic equilibrium, and then we derived the global form of Virial theorem. Then we applied this global form to a monoatomic ideal gas, right? And we obtained a very interesting relationship. Now what we are going to do is we are going to talk about the total energy of a star. Total energy of a star. You see, in order to determine the influences on the total energy of the star, we have to again consider the energy equation, and this time we have to integrate over the entire star. Okay? Yes. So this was the energy equation, okay, which we previously derived. Now what are we going to do? We are going to integrate this over the entire planet. And as a result, we will find this thing. This was equation 9, and this is new, continuing with our formalism. This is equation number 52. Now let us do the exchange of time derivative with mass integration. If we do that, then you will see we will have this relationship. Now I request you to do these integrations and calculations at home to check if this is really happening or not. And along with this relationship, we will, if you do continue the integrations and play with it, then you will also find this relationship as well. These two relations. This is equation 53 and this is equation 54. Okay, we are just playing with this, the derivatives, how they move around. Okay, it is not very hard, it is again not very straightforward as well, but you should try it at home. Now if we use all these equations that I have just shown you in the screen, then we will finally have this relationship, equation 55. Now you see this equation here, it relates the total internal energy U of a star to its nuclear generation rate here. So, and what is this? This is luminosity. So this relation, it basically relates the total internal energy with the nuclear generation rate and the luminosity. But again, this part is still not finished. It is still there. So one integral remains to be evaluated. Okay? So that this equation you see here, it depends only on global quantities of the star. This is what we want. Now, in order to evaluate this integral, let us return again to the equation of motion. So what we did this time to find the total energy of the star, we first used the energy equation, integrated it over the entire star, and now we are going to integrate the equation of motion again over the entire star, and then remember, after multiplying it by r. Now if we do that, then we will have these relationships, you see. So this, we are doing all this effort to find that integration. Now the first integral over here, this one, this can be evaluated to obtain this result, you see. K dot, the final result, you see, this is K dot. And what is this K dot? Basically K here is the radial kinetic energy, you see, which is also the total kinetic energy, since we have assumed spherical symmetry. Now let us work out the second integral. Similarly, we can also evaluate the second integral to get this result, equation 58 here. And what does this gives us? This gives us in terms of the gravitational energy, right? Dot product ddt of the gravitational energy. And so finally, if we use these results, we have this term. Let us use this together, equation 59. Thus what we did is that we have found an equation which relates the total energies of the star, U dot plus K dot plus omega dot is equal to L nuclear minus total L. This is a very important relationship. So we have basically derived this relationship. Now note that since this L nuclear minus L luminosity is a measure of the net loss or gain of energy in the star, we can define the total energy of the star to be E is equal to U plus K plus omega, and thus this above equation becomes what? E dot is equal to L nuclear minus L. Okay, let me again write this down over here, just a second. Okay, now the first thing to note that if L is not equal to L nuclear, what will happen? Then the total energy must change. Now, what happens in case of thermal equilibrium? In case of thermal equilibrium, then L nuclear is equal to L, right? Let me write it. These are interesting results. These are basically the fruits of our endeavor. So, what I was saying is, if total luminosity is not equal to L nuclear, then what will happen? Then total E must change, right? Now, if star is in thermal equilibrium, thermal equilibrium meaning L is equal to L nuclear, right here, then what will happen? We will get from the previous result E dot equal to 0. Now, if it is also in, again, so if star is also in hydrostatic equilibrium, then what will happen? K dot equal to 0, hydrostatic equilibrium. Thus, from the Virial theorem, okay, now, so by the Virial theorem, what we will have? We already have, we will get this result. Therefore, what does this mean? This means that if a star is in both thermal and hydrostatic equilibrium, then U dot equal to 0 and again omega dot equal to 0, which means the star cannot expand and cool, nor can it contract and heat up. So let me write it down, this result. So the result is, if a star is in both thermal equilibrium and hydrostatic equilibrium, then we just observed, what did we see? We just observed that U dot equal to 0 and omega dot equal to 0, which means the star cannot expand and cool, nor can it contract and heat up. Okay. Now, it is also important to note that because as we have this relationship, so we can set where alpha is a constant of proportionality. Now, if the star is in HE, hydrostatic equilibrium, but no thermal equilibrium, then we will have E is equal to U plus omega, right? And so the total energy U we can write minus alpha omega plus omega. So this gives us so what do we get? Thus, if alpha is less than 1, then this is greater than 1, right? This expression. So this means that E dot is less than 0. and then U dot is greater than 0, and so the temperature increases. Remember that all reasonable stellar models, they satisfied this relationship, alpha less than 1. Thus, we observe that removing energy from a star will increase its temperature. So, removing energy causes an increase in temperature. What does this mean? This means that our star has negative heat capacity. Okay. Any questions till now?